Okay, good afternoon, everybody. Welcome back to the final two presentations for the second NASA Gregory G. Leptoukh Online Giovanni Workshop. This is your host, Jennifer Brennan. I've got just a couple minutes to 2 p.m. Eastern Standard Time, but I'd like to go ahead and get started. For those of you just joining the webinar this afternoon, I wanted to go over a few housekeeping items. The first is to ensure the best audio experience, the conference has been placed in silent mode. If you have any questions or any issues, please enter them into the Q&A pod, and you can see that on the right-hand side of your screen. Okay, this works like a chat. The webinar will be recorded and posted online after the workshop. Speaker presentation files will also be available for download at the end of each talk, but not only at the end of the talk, I've also posted all of the files from the entire workshop on our last layout, after the closing remarks, so you'll have an opportunity to download any presentations you may have missed earlier, okay? The program layout is as follows. Each talk is 1 hour long. We've got 2 remaining. 30 minutes are allocated to the presentation with a 15 minutes of question and answer period that follows each talk, and then a 15-minute break between the last 2 final talks. Questions will not be answered using the raising hand function. It has been disabled. Again, we'll take all questions using the Q&A pod at the end of each presentation. It is my pleasure to introduce our first of the final 2 speakers this afternoon, Yangyang Xu. He is a postdoctoral researcher at the National Center for Atmospheric Research, or NCAR, in Boulder, Colorado. Dr. Xu?
Okay. Hi, everyone. This is Yangyang, and thank you, Jennifer, for the kind introduction, and also James Aker for organizing the event. I'm very happy to be here today and share with you some of my results, in particular using the Giovanni system. So for today's presentation, I will be talking about the carbonaceous aerosols and its radiative forcing over California region. But as I will show later, with the use of Giovanni system, the basic methodology here can be applied to basically other parts of the world as well. So I'm currently a postdoc at the NCAR Boulder, Colorado, but the work presented today was primarily done during my graduate school, so I want to acknowledge my graduate advisor, Ramanathan, and other colleagues from UC San Diego, as well as the external collaborators from Pacific Northwest National Lab. There are 2 papers basically published based on results today. One was on PNAS 2012 on the methodology part, and the second one on JJR last year on its application to California study. So I found out we have a very diverse audience in this workshop, so I want to spend a little bit more time in the background part to give the audience a broad picture of the motivation of our study. So I will introduce the concept of short-lived climate pollutants first, and especially one of the short-lived climate pollutants, the black carbon aerosol, including black carbon and organic carbons. For the methodology part, I will explain our new methodology of partitioning the atmosphere absorption into different species. And I will move on to discuss the application in getting black carbon radiative forcing using both observation and the modeling work. And that's the part the Giovanni system has been very useful. So first, the motivation part. What are the short-lived climate pollutants? There are several chemical species are categorized as short-lived climate pollutants, including carbonaceous aerosol of black carbon and organics, ozone, methane, and hydrofluorocarbon. And we call them short-lived species because their lifetimes only range from days to weeks and to a little a little more than 10 years for methane and HFCs, but still significantly shorter than the lifetime of CO2, which is decades to centuries. And we call them pollutants because most of them are also considered as air pollutants for their negative public health effects. Moreover, we realize they are also contributing to the anthropogenic climate change. And in terms of the present day related forcing, we can see the pie chart here. That's the energy perturbation due to addition of individual component. And we see the combined heating effects from those short-lived species can be as large as CO2. So it's not sufficient to just focus on CO2 for the climate change mitigation problem. We need to better understand those short-lived pollutants as well. To give you an example, we evaluate the contribution of short-lived climate pollutants to future climate change using a simple energy balance model. And we first consider a business as usual case in which the emission of CO2 and short-lived species keep increasing. So under such a business as usual scenario, the global mean temperature can go up to 4 degrees above the pre-industrial level. That's something not so good. And if we combine the emission reduction of CO2 and short-lived climate pollutants, we can effectively lower the temperature projection to be under 2 degree warming. And we can see CO2 and short-lived pollutants are contributing about half to the warming mitigation. And one thing to point out here is the timing of the mitigation effect. And even we started the CO2 emission control right now, its mitigation effects on temperature can only take place after the mid-century because of the longer lifetime, while the short-lived climate pollutant mitigation on temperature can take place right after the emission control measures started. And it turns out this early timing of mitigation effect due to short-lived species can have even larger effects on sea level rise. So this is another paper we published earlier. For example, we consider a similar business as usual case. Under that scenario, the sea level rise can be as large as 1 meter by end of the century. And if we want to do something to avoid the projected sea level rise, we can do two things. The CO2 emission control can only lower the lower the sea level rise by about 9%, but short-lived climate pollutants can lower the sea level rise by 22%. So we can see even the temperature mitigation effects being similar by the end of the century for CO2 and the short-lived species. The short-lived species are actually two times more effective in curbing future sea level rise. And the carbonaceous aerosol, in particular the black carbon, is one major component of short-lived climate pollutants, which I will move on to discuss now. So black carbon is mainly produced from the incomplete combustion of carbon matters, including fossil fuel, biofuel, and open vegetation. We can see the global emission of black carbon has been doubling in the past 50 years, mainly due to anthropogenic activities. And spatially, the emission of black carbon are very heterogeneous distributed, mostly concentrated over regions where open biomass burning are frequent, for example, Amazon forest fire and savanna burning over Africa, and over the developing countries like India and China, where the fuel combustion efficiency is low. So here is a nice diagram showing the black carbon processes in the climate system. Again, we can see there are various emission sources of black carbon, including agriculture, industrial, residential, and transportation. And many of them are not necessarily coming from the same source of greenhouse gases. So it's not that greenhouse regulation will automatically lower the black carbon emission. We really need to take some additional measures to tackle the problem. And there are many two ways of black carbon can affect the climate system. One through atmospheric heating, another through surface darkening. Uh, it, for atmospheric heating, it can directly absorb the incoming solar radiation and heat the atmosphere. And for surface darkening, after being removed from the atmosphere at the end of its atmospheric lifetime, black carbon can continue to influence the climate system because if it gets deposited over bright surface like snow or ice, it can effectively darken the surface albedo and produce a warming at the surface. So among all other aerosol species, black carbon is actually the only one that produces a positive forcing, namely warming the planet. We can see also the uncertainty on its positive forcing is also the largest one. The error bar of the total uncertainty of aerosols are almost entirely coming from black carbon. So as a first step to better understand the role of black carbon in the climate change, we need to narrow down the uncertainty of its radiative forcing. Here, the error bar from IPCC report are representing both estimate from models and observations, which means there are great discrepancy between the two. So I'm giving another example here. On the right-hand side is an early study based on observation done a few years ago. On the left side, on the left-hand side, I'm showing an example of model simulated black carbon radiative forcing with the present-day emission using one of the current generation of climate models. We can easily see there are large discrepancy between the two, and the model forcing is only about 1/4 of the observational estimate. And also there are great spatial difference as well. So the plot here is from one model, but there are many other models have reported similar under prediction. So my objective for this study is to understand the potential biases in the model by using observational data set. So let's first look at the two approaches in a little more detail. For the observational part, we use satellite data set to provide the total amount of aerosol optical depth. Basically, that's the total amount of aerosol, including black carbon and everything else. And because black carbon is the main absorber, we need ground-based network like Aeronet to obtain the absorption part of the optical depth. And the total absorption here need to be partitioned into different species because black carbon is not the only one that absorbs the solar radiation. We know organics and dust are also good absorber as well. And previously, for this partitioning scheme, we have to borrow some model-based information, so the approach is not entirely observational. And this aspect has been improved by our new method, which is purely based on the observational information. I will come to that in a minute. So for the modeling part, on the other hand, is basically a bottom-up approach. You start with some assumption of emission inventory, then use the chemical transport model to calculate the atmosphere concentration of aerosols over specific regions. And some optical parameterization scheme has to be used to calculate the bulk optical property such as AOD and ALOD, which then can be directly compared with the observation. And now, of course, for climate studies, we are mostly interested in the energy perturbation, the radiative forcing part that can be calculated by either online or offline radiative transfer scheme. So, for the methodology part, as I said, we developed a more objective method based on the observation to obtain the partitioning between different species. Without going too much into detail, this method basically is using the observation information of absorption at different wavelengths and use that wavelength dependence as a signature of the different chemical species. For example, here we're showing that for AAOD contributed by organic carbon is only about 40% of that due to black carbon at short wavelengths for 40 nanometers. But if you go higher to the larger wavelengths at higher wavelengths, the brown carbon absorption is only 10% of black carbon. So when I look at the program of this online workshop, I found similar ideas have been used by oceanographers who look at the ocean color remote sensing data set, and they were trying to understand the contribution of phytoplankton and non-phytoplankton component of the ocean color. I think that's basically the similar ideas. So for the rest of my talk, I will showcase a study which will apply this method into California. So there are multiple resources of satellite products available for our study, but they all have different coverage, spatial resolution, as well as limitation in the retrieval products. So we'll play with the satellite product for a while, and that's when the Giovanni system have been very helpful in the process, because we can easily make plots over specific time period and specific region and compare that with published result. So after some trial and error, we settled to use Miser, which is on board of Terra satellite over California, because it has better fidelity over California, which has a mixture of ocean surface and high reflectivity surface of desert region. And for ground-based network, we use a dataset provided by AeroNet, which is also maintained by NASA, but currently this dataset is not in the Giovanni system, so we have to do some additional work on that. For model, that's very handy because the GO card, which is NASA chemistry transport model developed at NASA Goddard Center, is also readily available through the Giovanni system. You can see here it output individual species from the model. And also we collaborate with the DOE lab at PNL to conduct the WRF-Chem simulation, which is a regional chemistry model that is fine-tuned for this California case. So let's look at the main result first. Here we can see we obtained the total AOD and the total absorption part of the AOD over the entire California region. For the total AOD, it has a larger value over Southern California, but for total absorption, it has maximum value along the coastline. And then using our partitioning method, we can find out the contribution of black carbon to the total AOD. You can see the spatial distribution is not entirely the same. The black carbon has maximum value in the Central Coast and Central Valley agriculture zone region. And one thing to note here is the magnitude. The black carbon AOD is only about 10% of the total AOD, but black carbon absorption AOD is contributing to about 70% of the total AOD. That's why we said black carbon is a major absorber of solar radiation in the atmosphere. And all the estimation here is done purely from the observation data set, including by using our observation-based partitioning method. But we know that black carbon is only one major component of solar radiation absorption. What about the other two? So here, the total absorption is partitioned into 3 components: dust, black carbon, and organics. For the top panel, we can see dust has a larger contribution over Southern California. And organic contribution is much smaller, but it's not negligible. And this is based on observation study. What about the model? Let's look at how this partitioning is done in the model. The go-kart actually overpredict the dust contribution by quite a bit. The dust contribution to absorption is even larger than black carbon. And the organic absorption is entirely missed by the model. And actually the fact that the organic carbon absorption is neglected by the model is not very surprising, because the experimental measurement of organic carbon absorption is just newly available. And traditionally, we consider organic carbon only as a purely scattering species, and now many lab measurement as well as in situ field campaign measurement are suggesting organic carbon are also a strong absorber in the UV band. So our study actually confirmed this point by using satellite data, that even we look at the large scale ambient environment, we can still find considerable amount of organic carbon absorption, which is here. And if we combine the absorption and model approach and to get a hybrid product, is basically telling the similar things, but in a medium value. So another way to compare the model versus observation is by looking at the one-to-one scattering plot. So here each dot is a seasonal estimate of seasonal estimate of AOD and AAOD. On the x-axis is the observation. On the y-axis are estimates from 2 models, the global model of go-kart and regional model of WRF. So we can see the NASA go-kart model actually did a fairly good job in the black carbon simulation, but not so well in the organic carbon. It actually overestimates the scattering part of organic carbon. But again, the organic carbon absorption is close to 0 in the models. But in the observations, it has a non-negligible contribution. The WRF-CAM run by DOE lab again underestimate both the black carbon as well as the organic carbon contribution. And again, the DOE lab WRF regional model also has no organic carbon absorption. So as a sensitivity test, we increase the emission factor in the WRF model by a factor of 2. When we double the emission in the WRF model, we find it's still quite off from the observation. So the model biases is not merely a result of the emission inventory. The organic carbon treatment in the model can be additional source of the biases. So here is the final product of our study. With the chemically resolved optical property, we can estimate the radiative forcing due to carbonaceous aerosol over California. That's the combination of black carbon as well as organic carbon. And we can compare that observed observational forcing with model simulation, including a global chemistry model and a regional model simulation with a higher resolution. We can see that even over California region, the difference between the observational methods and the model are still large, and both models can capture the spatial distribution to some extent, including the maximum value in the Central Valley and the maximum value in the coastline cities like LA and Bay Area. But the thing that we care as a climate scientist are the radiative forcing magnitude. And here, the worrying part is both models are underestimating the radiative forcing to some extent, even after we adjust the emission factor in the WRF regional chemistry model. So, uh, so here is we argue that organic absorption is something that models should improve on, and this have huge climate implication because we know that black carbon and organic carbons are often co-emitted species, especially from the biomass burning sources. So from a policymaker point of view, it's not an important issue for black carbon if much of its warming is largely masked by the co-emitted organic component. However, according to our study, at least in California, the organic carbon total forcing is largely close to zero, which means black carbon positive forcing dominates the equation here. The total combination of carbonaceous aerosol forcing is almost identical to the black carbon forcing. But this is just over California. What about other biomass regions like Amazon and Southern Africa? I think we can apply similar methodology to those regions as well, and the Giovanni system can be very useful for such studies. So to summarize, black carbon aerosol is an important short-lived climate pollutant. It has caused significant climate change in the past and will probably be important for the future climate change mitigation as well, especially for the near-term climate change mitigation in the next few decades. However, most of the global climate model that are used for century-long climate change simulation, for example, under the IPCC framework, has underestimated the black carbon radiative forcing. And we conclude, based on our study, the emission inventory used in the model can be one source of biases. Some future research are needed to further constrain the emission inventory here. Another important point here is the organic carbon absorption is another source of biases, and models should be improved in that aspect to improve our understanding of the total carbonaceous aerosol radiative forcing. So that's all I have today, and I'll be happy to take questions if any. Thank you.
Okay, thank you, Yangyang. We finished just a little bit, just a couple of minutes early. So what we will do now is we will move to the question and answer period. If you have any questions for our speaker, please be sure to post those, excuse me for a moment, and on the right-hand side in the Q&A pod. And as you can see in the lower right-hand corner of your screen, I've also uploaded his presentation. If you are interested in downloading, you'll just select the file, and then you'll have an option to download. Okay, so let's give all of our participants a couple of minutes for questions. Any questions for our speaker? There's got to be a question here for our speaker. Okay, here we are. So the first question is, are black carbon aerosols in California primarily anthropogenic or primarily natural?
Yeah, it's a good question. So based on our methodology, it's hard to tell the actual sources of black carbon aerosol. We're basically telling the total amount of black carbon aerosol in the ambient environment. But based on the modeling studies, they are assuming a big fraction of black carbon aerosol coming from anthropogenic sources instead of natural sources. The anthropogenic sources have been mostly from the diesel engine combustion from the mostly the trucks and off-road vehicles. But the natural sources, in particular the biomass sources like wildfire, which is going on a lot in the California region, can be a big contributor as well. But it's hard to quantify down to the actual sources based on our methodology here.
Okay, thank you, Yangyang. Any additional questions for our speaker? Okay. Move to the next. Nice comparison of model versus observation data. What features could be added to Giovanni to help with these kinds of comparisons?
Yeah, that's a good question. I think I briefly mentioned that point in my presentation. We've been using various data sets, including models and satellite, and those the comparison between those two are going very well through the Giovanni system. But another major data set we used in our study maintained by NASA, the AeroNet dataset, which is a ground-based network. So the data provided by AeroNet is not graded dataset. It's not graded in space and time. So I feel there might be some technical difficulty in incorporating that kind of information into the Giovanni system. But I'll be very glad if the NASA team can actually do something to add those informations in the Giovanni system. The AeroNet ground network is actually developed as a way to calibrate the satellite product. But it turned out after many years of operation, it has been a very successful of long-term monitoring of aerosol by itself. So it's very valuable data set and considered as ground truth for all the satellite measurement of optical depths. But again, it's not graded in space and time, so maybe there's some difficulty to put that into Giovanni system. So for our study, we had to do some additional coding and comparison to really compare the ground-based network versus the satellite data.
Okay, thank you, Dr. Shu. And the next question comes from our workshop organizer, Jim Acker, and he said, I remember that the LA area tried to put controls on grill fires, for example, like Burger King. Did they actually do this? And if so, did you notice any effect?
I don't really know if there's a law on Burger King, but the California Aerosols Board, that's the EPA California, has a very strict rule on the air pollution regulation. And one thing they have been putting out in the last 2 decades is stricter restriction on the diesel engine combustion. They actually enforce the installation of diesel engine filter to lower the black carbon emission from the diesel engines. And that has turned out to be very successful. In my 2013 paper, we actually made some estimate that over the last 20 years, because of the diesel engine restriction, we have effectively lowered the black carbon emission and the black carbon radiative forcing by a big amount. That has effectively mitigate the global warming contributed by black carbon, at least over this small region. But there are some push to scale up such a diesel engine restriction law to uh, other part of the country and even to the other part of the world, but it's still something ongoing.
Okay, thank you, Yangyang. So I have a question, actually. Are there any efforts underway that you know of that are designed to try to quantify um, the two sources of black carbon, so to distinguish between the anthropogenic and the natural sources in your region?
Yeah, there are some field campaign going on. They actually have to go for in situ measurement, and they try to measure the co-emitted species of black carbon and trying to use that as a way to distinguish between the two. For example, the natural sources of black carbon coming from wildfire is often associated with the some elements when we burn the wood. But for the diesel and other anthropogenic sources, it has some heavy metal co-emitted with such combustion. So they often use that as a way to distinguish the contribution of the two. But for climate science study, we're mostly concerned with the anthropogenic part because that's something that has potential to going up in the future or going down if we take measures to control. For natural sources of black carbon due to wildfire, we basically consider that something not going to change for the future climate.
Okay, thank you. I have a comment here from Jim Acker, and he said, also, have you seen the MAPS Statistical Explorer link on the Giovanni homepage?
Oh, no, I don't think I have seen that.
So Jim, I don't know, I guess you're not, are you dialed into the telecon? You might, further describe that as a tool. Oh, it's an AeroNet tool, he said. So maybe that's
okay.
something to check out,
Yeah,
later.
I also see the comments from Case Bryant about the Aerostat. Yeah, that can be very useful. Thank you for those.
Okay. Any additional comments or questions? Yes, Jim said thank you. For our speaker? We do have a few minutes. Okay, here we go. Great. Did you just look at temperatures for radiative forcing? What about net incoming and outgoing radiation?
No, that's actually something I want to clarify. For radiative forcing, it's defined as net incoming radiation. So everything I have shown is the perturbation to the radiative forcing, to the incoming and outgoing radiation. So the positive sign I shown for black carbon case means there will be more incoming radiation down to the planet, while less outgoing to the space. I didn't show anything about the temperature. We have some ongoing simulations for which we use the climate model to simulate how the local temperature and precipitation change in response to the radiative forcing, but that's not in today's presentation.
If you need me to, Dr. Shu, I can pull up your presentation again. I don't know if that's of value to the listeners.
Yeah, maybe the last.
Okay. And if you wanted to identify within your PowerPoint where, there you go.
Yeah, so for example here, everything here is radiative forcing in the unit of watts per meter square. And globally, It's estimated the global mean average of black carbon radiative forcing is about 1 watts per meter square. As a comparison, the CO2, current CO2 forcing is about 1.7. So some has suggested that black carbon is the second largest radiative forcing, just second to CO2. But some has said methane is probably larger. But anyway, black carbon can be important, and you can see locally for California, it's a lot larger than global mean. Sometimes it's even 3 to 4 watts per meter square. So locally, it can be an important heating source. But the temperature response at this local region is not only influenced by the local forcing. It can be influenced by the forcing over other parts, over our other region as well as the ocean surface nearby. So it's not entirely straightforward that the positive radiative forcing here will definitely lead to temperature increase. There's some additional work has to really test that point.
Okay, thank you, Yangyang. Are there additional questions for our speaker? I'll give it just another minute or so. If I don't see any additional questions, what we will then do is we will take a 15-minute break between this talk and the final talk for the workshop. I'll give it just a minute here. Just as a reminder, if you're interested in downloading his presentation, it is available in the file sharing pod in the lower right-hand corner of your screen. Okay, here's another question for you. Have you seen any seasonal variations in the black carbon levels?
Yes. Actually, I didn't show today, but for our paper, we include some of the comparison. And the seasonal variation actually is the largest for organic component, which we consider primarily from the natural sources of wildfire. So it's mostly for wildfire as well as the VOC emission from the forest. So it's primarily going on in the summer and fall season in the California. For black carbon, we didn't see much seasonal variation in the observations. And the anthropogenic source of black carbon in the model actually assumes some type of seasonal variation in their emission inventories, which is has larger emission over winter seasons, presumably because of the heating. But whether that's actual, whether that's something real in the observation, we didn't see that, at least from our study.
Okay, thank you. Very interesting. Any additional questions from anybody? I have to give people an opportunity to type, because, but we'll give it just a little bit and then